Okay, this is our example 2 in the section on the velocity of sound. It says if a thunder happens at an elevation of 20 kilometers, which is 20,000 meters from the ground, how many seconds will it take for us to hear it? Assume that the temperature of the air as a function of the height, as a function of the elevation, can be approximated by 20 minus 0.005 H, okay? This isn't the actual temperature of the air's function, but we're just modeling it as a linearly decreasing function. So what that would mean is on the ground, the temperature of the air would be 20 Celsius, and then as you go up, the elevation, the temperature is decreasing linearly. So at an elevation of 20 kilometers would be 20,000 meters, right? What would the temperature be? Well, we would have to just put here 20,000. So it'd be 20 minus 0.005, 20,000, right? 20 minus 0.005 times 20,000, and you get minus 80. So minus 80 Celsius. In reality, the temperature of the atmosphere of the Earth decreases for a while, then it actually increases back. Then it decreases and it increases. So it's kind of a wavy thing. It decreases, increases, decreases, increases. But I'm just assuming it decreases linearly, right? What would happen here in this problem if the temperature was constant throughout? If it was always 20 Celsius? How many seconds will it take for the sound wave to travel from that elevation to the ground? That one would be easy to calculate, right? T would be the distance divided by the velocity of sound. If the distance is 20,000 meters, then we divide it by the velocity of sound. And I'm assuming if the whole air had always been 20 Celsius, then we can use the velocity of sound at 20, which is 343.3. Then we would divide them, and this would tell us how many seconds that would take. 20,000 divided by 343.3. That would give us 58.26 seconds, right? So in our case, how many seconds will it take? Will it take more than 58 or less than 58, right? Well, if the temperature is decreasing here, then the velocity of sound is going to decrease, right? Up here it's going to be going slower. Then it's going to speed up as the sound wave is going down, then it's speeding up, speeding up, speeding up, right? So originally it's actually pretty slow compared to the ground. So it should take more time than 58, maybe 61, 62, 63 seconds, something like that. Okay, so how do we do this? So then we're going to use the equation is equal to 331.4 square root of 1 plus t over 273. Then we're going to put that equation that we have. So velocity of sound is going to be dh dt. It's basically the rate of change of the height, how fast the height is changing as a function of time. That's the velocity of the sound, right, as it's coming down. So then that's equal to 331.4 square root of 1 plus, and then the t is equal to, it would be the 20 minus 0.005 h, right, over 273. Then we have here dh dt, 331.4 square root 1 plus 20 over 273 minus 0.005 h over 273. 331.4 over square root of 273, and then make the square root of, and then what does this become? 273 plus 20 is equal to 293 minus, and then this is gone, this is gone, this is gone, right? 273 plus 20, 293 minus 0.005 h. Okay? So then the next thing I'm going to do is take the dt over here. So we have dh, and then take the square root down there, right? So dh over square root of 293 minus 0.005 h, that's equal to 331.4 over square root of 273 dt. Then integrate this, integrate this. Integrate this from 0 to t, right? We don't know what the t is. That's what we're trying to find out. And then integrate this from 0 to 20,000. Because the original height of the sound wave that it started its journey was 20,000 meters up, right? So this is an actual integral that we have to do, but this is, you don't have to integrate because, the integral here, we can just do it ourselves. It's a quick integral. So 331.4 over square root of 273, it's just t. Then we can just solve for that. Then we have to calculate what this integral is. So you go to your calculator, you go to the integrate function, and this one comes out to be 1.2899195 times 10 to the third. Right? That's the whole integral came out that. Then to solve for d, just multiply this by square root of 273 and divide it by 331.4. So multiply it by 273 to the power 0.5 divided by 331.4. 64.3 seconds. I have a big smile on my face. Why? Well, because we calculated that if the temperature had always been 20 degrees Celsius, it would have taken 58 seconds, right? So we said that it should take longer now because the velocity of the sound is slower up in the higher elevations, right? So it took about 6 seconds longer, right? 64.3 seconds for the actual thunder to come and for you to hear it on the ground. Okay? Pretty cool, cool. Awesome stuff. I love this. Okay? Thank you very much.